Hi. So we're finished with classical mechanics. We did 8 chapters of that. And now we're going to skip ahead to chapter 13. We will come back later on to do chapters 9, 10, 11, 12, but we'll only do some certain sections of those. And we may or may not do chapter 12, depending on time. Okay? So we're going to do chapters 13 and 14. These chapters are critically important for you to understand the material for physics 2. So these lay the foundations for physics 2. Okay. In this slide, I want you to think about, in this image, what kind of waves you see or you recognize. And then on the next slide, you'll find some answers for that question. Okay. So waves have to do with periodic motion. Anything that's periodic repeats at certain intervals, either at regular intervals in time or at regular intervals in space, or both. So there's something that happens periodically. Okay? It repeats periodically. In this section, we will have another look at Hooke's law. We studied some of Hooke's law before, and we'll revise that a little bit. And we'll talk a little more about it, how it's connected to waves. Okay? So in the periodic motion, what happens is you can have a disturbance at the start that gets carried forward in a medium. Okay? And that will generate a wave. Okay? We will see that towards the later part. So here's the answer to the previous slide. We saw water waves, guitar waves, light waves, and sound waves. If you thought heat waves, that is not correct. Okay? So the first system we're going to study is a spring mass system. Okay, so here's a spring. This is its normal resting length, and this is the mass hanging from it. We will neglect the mass of the spring every time. Okay, so I might not say this every time, but every time we're going to assume that the spring itself is massless. We know that this system, if displaced by a certain amount, so if I stretch it out, say to this level, so from its zero equilibrium position, I pull it down by a certain distance, uppercase x, okay? Then since it's downward, that's written as negative x, okay? And I let go, it's going to go back, and then it's actually going to shoot up the same distance to positive x, and it's going to oscillate about this position. So it's going to oscillate about equilibrium position. If there are any non-conservative forces in the system, they will dampen or they will make the system lose energy, and ultimately it will come back to rest in this position. So the forces on this, as soon as you let go, are governed by Hooke's law, which is this. Fs, which is a restoring force, is negative k times x, where k is the spring constant. And it is given by the stiffness of the spring. Okay? It's a measure of the stiffness of the spring and the material, etc. So it's a value that doesn't change, provided you have the same spring. X is the displacement, okay? Here, this lower x, that's what this is. What does the negative sign mean? The negative sign means that the system, the force on the system is such that it's always opposing the displacement x. So if I stretch the spring out by pulling it down, my force is trying to drive it back to the equilibrium position. Okay, so here the force is upwards, Fs. It's in the opposite direction to the displacement, which is downwards. At equilibrium, there's no displacement, so x is 0. When the spring is compressed, the displacement is upwards, and the force is back towards equilibrium. Force is downwards. So the force is always driving the system back to equilibrium. Okay? So we talked about this. Okay, so it's called the restoring force, always driving towards equilibrium. What happens is that the object is trying, the mass is trying to get back to that equilibrium position, but when it gets to x equals 0, it's moving so fast, it has so much momentum that it overshoots and it compresses the spring and keeps oscillating like that. So if there is no non-conservative force, if there is no non-conservative force, so there's no dissipation of energy, then this motion will keep on happening forever. Yeah? In reality, that doesn't happen because there's always air resistance, there are always frictional forces, and after a while, it comes to a stop. Okay. So unless we say that there are frictional forces, we're going to assume that there are none. So now it's that same spring mass system. It's oscillating up and down, okay? And that oscillation is shown here, okay? So this is the position of the spring at different times. This is its resting length. Then let's say it's compressed. So this is it at its maximum displacement upwards. It shoots back towards equilibrium, overshoots because it has too much velocity, and goes the equal distance to the other side. So this is maximum extension, goes back to equilibrium, overshoots because of momentum, and so on. So it starts repeating, this cycle starts to repeat. Yeah. If you just join up these points, you see that a wave is being generated over time. Yeah. All of these different positions are actually just happening right here. But over time, this is the kind of position that the object is following. Yeah. The same thing can be drawn out if you just attach a pen, say a green pen, to this mass on the other side, and you have a roller on which some paper is rolling at a steady rate with time. Then we see that this up-down motion gets stretched out in time because the paper is moving. So you have the up-down wave, and then it's moving forward. Yeah? Okay. So here's the same thing. We see this is our resting position, x equals 0. Okay. This is the maximum extension, x equals negative a being the amplitude, which is the maximum displacement. And here we're starting from the most compressed state, which x equals positive a. Okay. So if we plot the position of this object, yeah, with respect to time, let's say, and each of these is at a later time, then I start at positive a, right? I start at this one at positive a. So the green lines are just showing us the equivalence in time, okay? The position starts here. Next, we're at equilibrium, so we're right here on this line. Next, we're at negative a, so we're right down here. You can join these points together, and you begin to see that you're getting this pattern. Yeah, you can follow it through. Okay, so this maximum displacement, whether it's in the positive or negative direction, is called amplitude. Okay, you will have equal amplitude in both directions about the equilibrium position. Okay, another thing to note is what is one time period. That's one pattern, the time it takes for one pattern to repeat itself. Okay. So here we're starting from a maximum, going to a minimum, and back to maximum, right? And then the whole thing repeats again. So this is one time period, yeah, in terms of time. If this axis were space, like say the x-axis, this would be one wavelength. So one unit of the pattern is one wavelength in space. In terms of time, it occupies one time period. That's one entire oscillation, starting from most compressed to least compressed to most compressed again. And that's our one time period.